Welcome back to the channel. Just want to really quickly make sure that what's the word I'm looking for? That it looks good on YouTube, which apparently it does. Now, the reason why I am coming at you again today from my home is that I may have come down with something. I don't know if it's the Rona, but it might be. I've got tests on order, so we'll have to see how that goes. But that is not going to stop me from giving you my tour of the universe, or at least a portion. This episode brought to you by the good folks of water. Anyway, before I begin, and you may also notice I'm experimenting with background music. I don't know if I like it, but we'll see how it goes. If it annoys people, please let me know in the comments, or comments during the stream, or during the or in the commenting section. Wow, this is gonna be an excellent stream. I can tell already. So let me start off by actually talking about giving you an update of our observatory at George Mason University. So we are in the process of kicking off our spring semester, and we have a couple of exciting changes that we're going to be making. Well, one, I have actually, this is not quite a change, but I have taken over our Evening Under the Stars event, which is an event that we host here at our observatory on Tuesday evenings, starting at 7 Eastern. And I think that's midnight UTC. And what we do is that we give a public talk by someone in the community, either an astronomer or a journalist or a citizen scientist, someone of that nature. And that person speaks for about an hour or so, and then we give a tour of the observatory itself. The tour is is meant to be in person, but we do provide a short virtual tour as we transition from the talk to the observatory proper. So if you are not local, please, I would Google Evening Under the Stars, GMU. First hit you see brings you to our observatory page or event page. The first date is this coming 7th. The next one will be the 21st, and then there are subsequent dates further on down the line until early May. But that's probably not the most exciting thing. The most exciting thing is we're switching over to a set public tour hours. Now before, and we are still doing this, but in the days past, you could go onto our website and you could arrange for a private tour of our observatory. Well, we've been getting so many asks about private tours. We are almost running them every night, thereabouts. So we decided, why not actually just schedule an hour every Thursday, Friday, and Saturday, and just have it open. So if people want to, they can just come by and look through our telescope. Again, you can always, yes, Luna, you can still schedule a private tour outside of those hours, but we are now basically open for business for those 3 days. Luna, I don't know what you're doing, but I'd like you to stop. All right, whatever. Anyway, the joys of having cats. Where was I? Public tour. But tonight we are having a special event in that some of you may have noted or may have heard about the Great Green Comet that is currently flying through our skies. This is the first naked eye comet to be seen in our skies for a very long time. And this particular comet is what we refer to as a long period comet, in that it won't be seen again for about 15,000 years. But what's really peculiar about it is that, like I said, it is green. And the reason why it is green is because it has what we believe that in the nucleus of the comet, basically the comet proper, is an element is diatomic carbon. Now, when diatomic carbon gets excited by energy from the sun smacking into it, it glows a greenish color. Very similar to if you were to put particular chemicals into a Bunsen burner, the flame would change its color. In an analogous way, essentially what we're looking at is light from the sun makes diatomic carbon green. Now, I say it's naked eye comet, and that is technically true, but in our day and age, with the light pollution that we have, it is actually, you have to have a really, really good sky in order to see it. What I mean by really, really good sky is that we had a gentleman by the name of Hipparchus some hundreds, thousands of years ago. Basically, he categorized the sky, and he said all the brightest stars in the sky are first magnitude. All the dimmest stars in the sky are sixth magnitude. So imagine you had a Greek philosopher standing out in a Greek field when the brightest thing around him may have been a campfire somewhere else down the hill. So his sky was amazing. So we're talking about sixth magnitude is the limit of what the human eye can see if there is no light pollution anywhere around. The comet currently is around fifth magnitude, meaning that it is a little bit more than twice as bright as that faintest limit. From a practical standpoint, if you are viewing this from somewhere in the west, if you're in a desert, or if you're in basically West Virginia, somewhere that there is no, where you have a very good sky, then you might have a proper chance of looking at it with the naked eye. It's going to be in or about the area of the Big Dipper. But you can certainly look at it through binoculars, and you can certainly look at it through our 32-inch telescope, which brings me back to my original kind of point, is that we are starting out our public events, our public tour, tonight at 6:30 at George Mason University Observatory. So if you're in the DC area, please swing by and come look through our telescope for free. We have a number of our graduate students and our tour guides who are very knowledgeable about our observatory will be there to help you with that experience. Unfortunately, because of whatever it is I've come down with, I will not be there in person, but I do, depending on how well I'm doing later on, my intention is to live stream that event in some way whatsoever. And I'm hoping that maybe at some point I can get my grubby little hands on the telescope and actually start taking digital photographs of it. So stay tuned for that. So yeah. So that's what's going on with our observatory. We've also recently got, if you do come to our observatory during these public nights, we are sort of debuting our donation we received over the winter, which is a Nexstar 8 Celestron. It is an 8-inch Schmidt Cassegrain. It is a beautiful scope, and with all the eyepiece accoutrements and you would possibly ask for. So we are slowly building our arsenal of smaller but larger telescopes between the 8 to 12 inch range. So yes. Speaking of our observatory and possibly supporting it, if you would like to support our observatory, you can do that through moi. I do have a Patreon account, and all the proceeds of all the monies that go from the Patreon account will go back into the Friends of the Observatory Astronomy Club and also the observatory itself, so that we can start doing these events more often. We might be able to even expand our public hours to every day of the week or something of that nature. And of course, if you like these lectures, if you like the content that I put out, please like, share, and subscribe so that the observatory can get even more. Now, this is supposed to be a lecture, so let me use you see the chat? At least tell us. Oh, sorry. I was blocking out the. Oh, hello, 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 hello. Can you hear me now? Can you hear me now? Now. I was blocking out the chat because it makes my face really, really, really bright. Can you hear me now? Turn off the music. That's probably it. Pause. How about now? Can you hear me now? Now. No. Okay, so the music idea sucks. All right. Thank you. Thank you very much. Thank you. All right. So yeah, I couldn't see because of the were you able to hear anything at all about the announcements that I made about the public nights or the public hour and the observatory and all that? Oh, and hello, Rachie. Hello, Judy. Hello, Dr. Nimrod. Chris, always fine to see you. Maybe I could convince Chris to give, provide some background music for the show that isn't so crappy. I didn't realize it was that loud. Okay, you heard most of it. Point is, I might be the Great Green Comet that is currently in the night sky. I may be doing a live stream later tonight, depending on how I feel. I am coming down with something. But if you're in the DC area, again, please come by our observatory and look through our telescope as well. So, all right. Yeah, I don't know. I had this inkling of maybe sprucing things up a bit with maybe some music, but apparently that's just a really, really horrible idea. So anyway, but like I said, since this is theoretically supposed to be a lecture, let me actually put up a lecture. So this is a presentation that I typically give for folks during during certain public events that we have at the observatory, and I'm going to modify it a little bit because I think it is a very good sort of starting point in showing what it is that we're going to be doing, or what it is I'm going to be doing through this lecture series, what the topics that I'm going to be highlighting. Now, it is a little bit of a misnomer in that I'm going to only be doing basically up to the solar system. So it's the tour of the solar system. Tomorrow I'll finish it off just for giggles. But for the purposes of the solar system class, I will just simply be doing the tour of the solar system. All right. Okay. So Dr. Nimrod, let me go over that again. So without the music this time. So the Great Green Comet, as I'm calling it, it has a very romantic name of Comet 2022 EFTZ3. I don't really know. You can look it up. It's all over the news. But what I can tell you is that it is very, very faint. It is technically able to be seen with your eyeballs. It is a magnitude of 5, around fifth magnitude, when the lowest limit is about 6th magnitude. So it's about 2.5 times brighter than the faintest thing that you can see with your night sky. So technically, you can't see it with your eyeballs, but you have to have a really, really dark sky. I don't know how it is in rural Ireland, if you can get out to the country in Ireland, what the skies out there look like, assuming that it's even clear. Um, but what I recommend is getting a pair of binoculars, getting your hands on a pair of binoculars or something like that. I'll get to Pluto. Don't worry, Clive. I will get to Pluto. But the comet is going to be in the Big Dipper, or in or around the Big Dipper. And so, you know what? At the end of this stream, at the end of this lecture, which I should really get to for my students, I will go into exactly where the comet is going to be and how best to view it if you can't get to our site. So, but yeah, technically it is actually going to be naked eye, as it were. But enough of that for now. So, as always, if you've watched lectures of mine before, you know that I love starting off with this image. I'm really not going to belabor this, but this is the pale blue dot. That is an image of the Earth as taken from the Voyager 1 probe out at about 64 billion kilometers, thereabouts. Really, really far away. I think it's around the orbit of Pluto, which is still a planet, by the way. In Rob World, it's still a planet, and honestly, in my professional opinion, it should be classified as a planet. But I'm sure I will get into that in more detail when we get to old Pluto. This is our sun. So I'm going to start off with basically the center of our universe, as it were, the sun. And really what this slide is meant to show is that each of these slices that you see is an image of the sun as it is, basically simultaneously. So all of these pictures were taken at the same time. They are, but each of them, the reason why they look weird is that each of them is taken through a very narrow band of light. Either that light is in the visible range, like if you look at the very bottom, the orangey part of the sun, that would be what your eyes would see if you were looking through a properly protected telescope. But the other slices range in different wavelengths. And really what that translates to is you're looking at the sun at various temperature regimes or various energy levels. So if you're looking at the infrared, you're really looking at the lower energy phenomenon. If you're looking at it in the ultraviolet, then you're seeing the higher energy phenomenon. So for example, sunspots. Sunspots are magnetic features. The sun has an immense and complicated magnetic field. And sometimes that magnetic field gets all twisty. That is a technical term. It essentially knots back in upon itself, and it creates localized areas of enhanced magnetic strength. And what that does is it causes the outgoing flux, the outgoing energy from the sun, to be inhibited. It basically it doesn't quite block it fully, but it prevents a good portion of it from leaving the photosphere, the surface of the sun at that point. That energy doesn't go away. It doesn't get blocked indefinitely. It actually finds its way around to the sides of the sunspot. But it does in localized areas cause the sunspot to look less bright. And that's really what we're seeing here. Is the reason why it looks dark is that its temperature is less. So the average temperature of the sun, the surface of the sun, is around 5,880 Kelvin. Sunspots, the depth of the umbral part, or the darkest part of that spot, is around 4,000 Kelvin. So if you were to pluck that piece of gas out and put it into the sky, it would shine like a star. But because of the way cameras work, this camera doesn't have the dynamic range to really be able to show you a color or a temperature difference of around 2 grand in terms of Kelvin and Kelvin. But these are seen with your best in the visual range. This is a prominence. This is another magnetic feature. This is essentially energy. We have magnetic fields that sometimes pop out from the surface of the sun and cause these great arcs. This is actually material. This isn't material popping up and forming that arc. It's actually material condensing in the atmosphere of the in the coronosphere, and chromosphere. That's the word, chromosphere, and actually raining down. Later on, I'm going to be actually showing. Well, when I get to the sun, I'm going to be showing a video of this. It's freaking amazing, watching the solar material just rain down onto the surface of the sun, and you can see the Earth to scale. Now, this image was taken in the ultraviolet because, again, you can see that it's a higher temperature phenomenon, and it is better viewed. It can be viewed in the visible, but it's better viewed at higher temperatures, or higher. It's better viewed in light ranges that are more sensitive to higher temperatures. This is a flare, again, another magnetic feature, very hot, very powerful. But that's it for pretty much that's it for this for the sun. We're going to be talking in terms of the sun. Really, in terms of the sun, we're going to be talking about all the different factors of the sun. If I may close out with this picture of the sun, this is what's called multispectral analysis. When in astronomy, we don't just look at white light. We don't look at light that you can see with your eye. We look at light in the infrared regime. We look at light in the radio wavelengths. We look at light in the gamma rays and the X-rays. The reason for this is that it allows us a more complete picture of what we're seeing. What we see with our eyes is only a small, tiny fraction of what is going on in the universe around us. If we want a more complete understanding of what we are experiencing, then we need to look at other wavelengths. To give you sort of a terrestrial example, if I'm sitting here, and so obviously I see my cats sleeping up there, the lights and all that. But if my eyes were sensitive to radio, I would actually be able to see the Wi-Fi signals that are allowing me to talk to you right now through this. So I can only imagine the kind of what my reality would look like if my eyes were able to see in different wave bands. Looking in these different wave bands, that is what allows us to create models that tell us things like just how much energy is actually coming out of the sun over all wavelengths. And if we know that, then we can figure out how much mass is required in order to power the nuclear furnace in the centers of these stars like our sun. So multi-wavelength analysis, which I will be highlighting throughout these lecture series, is of vital importance for astronomers to be able to determine these things that I'm going to be talking about. Now, this, believe it or not, is Mercury. Speaking of multi-wavelength or multispectral analysis, this is not Mercury. You might be surprised that this is Mercury, because if you've seen Mercury, if you were just to do a quick Google search about Mercury, what you'd see is something that looks very similar to the moon. You'd see something gray and dull and really kind of boring. Side note, we had a speaker when I was a graduate student who was saying, hey, we're about to go send a probe to Mercury. And my department chair at the time, who always sleeps through these colloquia, he actually popped up and said, why? It's rock. What are we expecting to do from there? Personally, I thought that was hilarious because of just how very wrong he was. And what's funny about it is that his specialty was solar system dynamics. But anyway, this is Mercury as seen using, I believe this is ultraviolet. I will need to check. And what we're seeing here, what this allows us to do is it allows us to look at the particular chemical features of the rock that composes Mercury. Mercury is not just a rock; it is a solid body that is composed of a myriad of different materials. And this material, and what this material tells us, is what material there was in the solar system during its formation. Mercury is very weird in that it has a much larger iron core than would be expected for a terrestrial planet. We suspect that it has a very violent past, which is the reason why it's so much smaller, and so has such a higher ratio core. And I will get into specifics of that later on. This, of course, is Venus. When I was coming up, Venus was often referred to as the sister world to Earth. I don't hear that so much, primarily because I think we now know better. The reason why it's called the sister world, or was called the sister world, is because it has nearly the same radius, it has nearly the same mass density as the Earth. But it really could not be more different than the Earth, unless the only way that it could be any more different than the Earth is if it were a gas giant or a gaseous planet. Venus, named after the god of beauty, is anything but. It is, imagine the Earth, but instead of a lovely oxygen, nitrogen-rich atmosphere, its atmosphere is almost entirely composed, around 99% of the atmosphere of Venus is carbon dioxide. And it is very, very dense. The surface pressure of Venus is 90 times the surface pressure that you are experiencing right now. It's so high that there has only been one lander that has successfully lived for longer than a moment on the surface. There's only been one probe that has successfully landed on the Venusian surface. The Soviets actually managed to do it. I think it was Venera 2, and it lasted for about an hour before it was crushed like a tin can. Not only is the surface pressure one of the reasons why probes don't get down there don't last very long, but one of the reasons why it's sandy colored is because there's sulfuric acid in the clouds of Venus, and it rains sulfuric acid rain in the upper atmosphere. So if the probe can get through the massive amount of pressure, if the probe can dodge or not melt through the sulfuric acid, then it also has massive lightning storms that it has to deal with. So, but if it can get through all that, it could get down to Venus and see a world that is, in a sense, very, very young. One of the open questions that we have about Venus is that the Venusian surface appears to be very young, in the sense that it has remade itself within the last 100,000 years or so. The Earth's surface is exceedingly young because of things like plate tectonics, because of things like volcanism. It's constantly recycling the Earth's crust. Geologically dead worlds like Venus and Mercury, and to a certain extent Mars, they should have an older surface because there is no volcanism to really recycle that crust. And so the fact that it has a relatively, or astronomically speaking, young surface is a bit of a mystery. Yes, I'm ignoring Vulcan. I believe Vulcan was supposedly the Earth that's on the other side of the sun from us in the exact same orbit. I don't know. It's hard for me to keep up with these things these days. Moving on from Venus, we get to oh, I'm sorry, that is Venus. It took me a second. This is the surface of Venus, as seen, again, not by looking at the visual part of it. This is what Venus would look like if you were to look at it through a telescope, a very, very powerful telescope. This is what Venus would look like if you were to look at it through a very, very powerful radio telescope. In fact, this image was constructed by images taken by the Magellan spacecraft, which did radar pulses, basically radar sounding through the atmosphere of Vulcan. Vulcan. Great, thanks, Clive. Did radio? It sent radio pulses through the atmosphere of Venus. Those radio pulses impacted into the surface, bounced back up to the satellite, and we were able to interpret that data like sonar. And so we can get a very nice map of what the Venusian surface actually looks like. And we see mountains, we see canyon features, we see volcanoes, possibly active volcanoes, more than likely. More than likely dormant volcanoes. But like I said, it's an incredibly young surface for the type of geology that we expect for that planet. What we have here is, actually, this is an asteroid. I'm going to skip over. This is Ida. I'm going to skip over that. That's kind of not in order. I'll come back to asteroids in a second. This, of course, is Mars, Elon Musk's weird obsession. What we can see here is that Mars is fascinating for a number of reasons. It has captured the imagination of the human race pretty much ever since Percival Lowell thought that there were canals on Mars that changed with seasons. And as we look closer and closer to Mars, we realize that Mars may have in fact been habitable, kind of Earth-like in the first few billion years of the solar system. Now it's pretty much dead. There may be life on Mars, particularly microbial life that is beneath the surface that can be protected from harmful UV radiation. But the moment we got bupkis. We do have very, very strong evidence that liquid water existed on its surface, which would make it the only other world that we know of where liquid water has been on the surface of the world. The Earth at present is the only planet that we know of where water lives, can survive as a liquid. Water itself is ubiquitous. We find water all over the place in the solar system, but almost always it is in solid form, not liquid. The most distinguishing feature of Mars is what you're looking at right now. This is the Valles Marineris. Later on, I'm going to play basically an animation of what it would look like if you were to fly through the Valles Marineris. This is the largest canyon feature in the solar system. Mars actually has two largest sort of titles. One, the Valles Marineris is the largest canyon feature in the solar system. It also has Olympus Mons, which is the largest volcano in the solar system. Olympus Mons is, if you were to put it on the Earth, the entirety of the volcano would actually fill up the state of Arizona. Valles Marineris is actually, if you were to place that into the United States, or if onto the Earth, it would be as long as the continental United States. So the Grand Canyon ain't got nothing on the Valles Marineris. It is around, at the deepest point, is roughly 4 kilometers deep, and as I said, it's about the size of the continental United States wide. Unlike the Grand Canyon, which is an erosionary feature, it has taken the Colorado River many, many millions of years to dig out the Grand Canyon in all its glory. The Valles Marineris is not an erosionary feature, or at least we do not believe it to be so. We believe it to be a tectonic feature, which again is very peculiar, because what we're talking about here is that for some reason, which we don't fully understand yet, the Martian surface cracked such that it broke open and just basically scarred itself by pulling the crust apart and creating that large cavern feature. One of the fun things about Mars is that it can get, it can change its appearance very, very quickly, in the sense that it has dust storms. If you've ever been into a desert environment, such as the American West, occasionally you will have dust storms that pop up. People in Saudi Arabia have to worry about these all the time, from my understanding. But dust storms on the Earth are fairly localized. They, cover an area of a few square kilometers or so, or maybe even larger. I'm not entirely certain. What I am certain is that dust storms do not cover the entirety of the planet. Here, what happens is that while the atmosphere of Mars is very, very tenuous, it is dense enough that it can actually produce winds that will pick up the iron oxide dust on the surface and then circulate it across the entirety of the planet. And so in June of 2001, we had a very nice clear view of it. These are Hubble images. Very nice clear image of the surface. You can see the white is not, in fact, actually not entirely the ice caps. Actually, that is condensed carbon dioxide in the atmosphere. If you look close enough near the poles, you can actually see the land masses themselves. But you basically get a nice little nice view of the surface. Whereas a few months later, it had a global sandstorm, which really blocked out everything. These sandstorms are really the limiting factor to our exploration of Mars, because the probes that we've sent to Mars are solar powered. And while they do have, in some cases, have nifty windshield wipers that actually blow off or knock off the dust off the solar sails, they're not 100% effective. And so eventually enough of this dust will actually cake onto these solar cells and really just power them down. If we were somehow able to get somebody or another rover out there to actually, windshield wiper these things, we can power these rovers back up again. So who knows? So yeah, last thing I'll say about Mars is that again, I kind of gave it away. The reason why it's the red planet, or really the peach planet, is because it is literally rusted. The reddish color comes from the fact that there is iron on the surface, which has rusted because of the previous existence of liquid water, and iron oxide covers the surface, making it red. This is one of the various selfies. This, I believe, is Percy. Actually, no, I take that back. Yes, this is Percy, and it is an image taken of Percy by Ingenuity, the helicopter that deployed from it. Ingenuity itself is the first, again, another first for Mars. Ingenuity itself is the first powered aircraft to be flown on any other world but the Earth. So it is the first powered aircraft to be flown on a different world. And that in itself is an achievement, because NASA wasn't really certain that the Martian atmosphere was actually dense enough to allow for flight, that the propellers of Ingenuity would be sufficiently strong enough, or at least the air would be sufficiently dense enough to actually provide lift for the aircraft. So simply based on the fact that it actually flew, told us a great deal more about the Martian atmosphere than we knew before. Or at the very least, it confirmed what we suspected about the Martian atmospheres. Beyond Mars, we have the asteroid belt. Now, the asteroid belt is a belt of asteroids which is continuous. It's a continuous flattish disk in between Mars and Jupiter. One of the sort of scenarios that gets bandied about, and sometimes it gets bandied about with a certain amount of authority that shouldn't be there, is that the asteroid belt actually represents a planet that was destroyed at some point in the early solar system. That's not accurate. What is accurate is the asteroid belt gives us a glimpse of what the solar system, or the disk surrounding the sun, looked like in the primordial days. This is the stage of the this is the stage of planetary evolution where the dust grains in the early part of the disk actually coalesced into larger rocks, like asteroids. These asteroids would then slam into each other, either break apart into smaller asteroids, or if they were lucky, they would melt together in a bonding of love, or what have you. They would melt together. They would get larger and larger and larger, and eventually form planets. Now, the issue with no, unfortunately, that is in fact not Alderaan, but that would be cool if it were. What happened here? More than likely, what happened here is that Jupiter happened. Because Jupiter is so massive, it literally threw its weight around. This was a band where planetesimals were basically funneled, or asteroids were funneled into this ring, were gravitationally captured by through an interaction of both Jupiter and the Sun, and they were basically collected in this area. And it's that gravity that actually stopped any of these rocks into slamming together and creating a larger planet. So if Jupiter had been further out, possibly another rocky planet could have formed in or about that area. We don't know. We'll never know. But it was Jupiter's influence that constrained these rocks into this asteroid belt. It was not but it was never an actual planet of any size. Also, one of the many things that Star Wars gets wrong, in this case Empire Strikes Back, is navigating through an asteroid field is actually rather easy. The average distance between asteroids is about 1 kilometer. So unless the Millennium Falcon is really, really huge, flying through it, you probably wouldn't even be able to see two asteroids that were close to each other. So the odds are actually pretty great to actually get through it. This, of course, is Jupiter. Jupiter is the first of our Jovian worlds, or again, nomenclature in astronomy keeps changing. When I was a wee grad student back in the day, we just called them the Jovian planets, or the gas giants. But now we've separated things out. Jupiter is one of the Jovian worlds, but it is actually one of only 2 gas giants. It is, like I said, an immense world. It is 300 times more massive than the Earth, and you can place 100 suns from one edge of Jupiter to 100 Earths from one edge to the other. It is amazing in a certain way. It is amazingly very similar to the Sun. It has an almost identical composition, chemical composition of the Sun. It is almost entirely composed of hydrogen and helium, but it is composed of heavier elements like ammonia, methane, and other hydrocarbons and things of that nature. And that is what gives its color. Jupiter is also very, very rapidly rotating. Its rotational period, or one Jovian day, is about 11 hours long. So it's rotating a little bit than twice as fast as the Earth. Because of its fast rotation, and because of the fact that it's primarily composed of gas, that is what creates these beautiful windstorms that we see, these swirling effects. If you ever doubted that Coriolis was a thing, Jupiter basically tells you, yes, it is very, very much of a thing. We have these large cyclonic storms, the largest of which would be the white patches, the largest of which is the Great Red Spot. The Great Red Spot is unusual because, 1, it's red, and 2, it's so long-lived. Typically, these smaller storms that you see, these white storms, they can last maybe months, possibly even years. We have records that show that the Great Red Spot has been around for over 300. And even though there was some indication that the Great Red Spot was shrinking, that shrinkage appears to have stopped. So one of the open questions that we have is, what exactly causes the great red spot, and more specifically, why is it that it has such longevity? What is the energy source needed to generate that kind of power? I think I just answered that question. We don't know. Well, for at least the Great Red Spot, we don't have a clear understanding. For the smaller storms, what we believe is the energy comes from shearing of different atmospheric layers, uh, causing those cyclonic storms. Jupiter, Jupiter, unlike the other planets, actually does generate more energy than it receives from the sun. All the other planets, the reason why we can see them is because of reflected sunlight. They actually receive more solar radiation than they produce themselves. The Earth produces its own radiation, besides what comes from the sun, from radioactivity, but also from gravitational collapse. Because the Earth is still slowly contracting under its own mass, that contraction is producing a tiny bit of energy. For Jupiter, because again, it is far less dense, it has a density close to water, or 1 gram per cubic centimeter. That kind of gravitational contraction is a little bit is more pronounced, and so more energy is being generated in that sense. And so those local storms may be driven by asymmetries into that collapse. What wavelength is most of that energy at? For the storms, it's in the radio. But we will be getting I will get into that more when I talk about Jupiter specifically. You can actually, as an aside, you can actually buy a little kit known as Radio Jove. It's very simple. It's a very rudimentary radio receiver, and you can listen. You can literally listen to Jupiter, and it sounds kind of like a horror movie. This has really not much to do with the storms. It has to do the wavelengths that it looks at actually are sensitive to the fact that Jupiter has a massive magnetic field, and that it captures particles or captures electrons being shot out from the sun. These electrons then get accelerated very, very quickly between the poles, and it generates what we call synchrotron radiation. And that synchrotron radiation actually sounds like screams. So if you were to listen to Jupiter, it sounds occasionally like it screams every, I wouldn't say periodically, but every so often, Jupiter sounds like it's screaming, which is, like I said, kind of spooky. For the sake of time, let me push back that. Here, all right. Cyclotron. It's not cyclotron. It's how to spell? Copy. Mark again for the win. Cyclotron radiation. And also Stark Otter for the win. All right, so this is perhaps one of my favoriteest objects in the solar system, at least top 5. This is Io. This is the closest moon to Jupiter. It is one of the Galilean moons, or the moons first discovered by Galileo through his telescope. The reason why I love this moon, it is the most geologically active world in the solar system. It is constantly erupting volcanically. It's erupting right now. It erupts all the time. There are volcanoes that blow off all the time. It is also one of the smelliest worlds that you could possibly imagine. A great deal of that surface, the reason why it looks so orangey is because it's covered in sulfur. So it basically smells like rotten eggs. But It is, yes, I agree with Mark. It is a beautiful world. The fact that it is so geologically active just fascinates me. The reason why it is because Jupiter again is throwing its mass around, and it's basically squeezing it like a stress toy. Yes, I do believe you are correct. H2S. This is Europa. Now, Europa is the next planet or the next moon out. It is what. Excuse me. It is Europa is the next moon, next Galilean moon out. It is an ice world. What is now being considered an ice world. The reason for that is because we are now starting to see exoplanets that are reminiscent of what we see with Europa. With Europa, what we're seeing is something that has a rocky core, probably iron, surrounded by not a liquid hot surface of magma around it, but its mantle layer is actually going to, and it's actually we believe its mantle area is salty water. Basically a vast ocean underneath a very, very thick, 20-kilometer thick crust. And because of its rotation, it is synchronously locked. It rotates once every 7 days, thereabouts. Because of that salt water, that allows it to create its own magnetic field and its own heat. And so we believe that there may, in fact, the conditions may in fact be ripe for life to exist. Now, again, who knows? It could be microbial, but I like to think of, that underneath the surface there are hairy octopi and two-headed whales swimming around. Who knows? Maybe a race of mermen are underneath there. Who knows? The most striking feature of Europa are, of course, those reddish streaks that you see. Those are geologic in nature. Because you can have instead of there's cryovolcanism, which is basically volcanoes that spew out ice and water vapor, but you can also have sort of cryogeology, where the surface of Europa is also being squeezed like a ball, like a stress ball by Jupiter, and it causes that ice crust to crack and to spread out and create these lanes that you see here. The reddish color is, again, this really just is so cool. That reddish material is not native to Europa. That stuff is native to Io. Because Io is so volcanic and so explosive, that material that comes from Io gets blown out into space, and some of it lands on Europa and sticks into those canyon features, presumably because they're wetter. Then when they get formed, there's more energy that is being released during these events, and the ice is wetter, and so the material sticks better. So what you're seeing here is if Io did not exist, you would not see those reddish features on the surface, which is awesome to me. It's a great example of how one world can affect another. This is Saturn, obviously. Saturn is another gas giant, is the other gas giant. It has a very, very similar composition to Jupiter. It has the signature feature that it has the lowest density of any planet in the solar system. Its density is lower than that of water, lower than 1. And so if you had a bathtub big enough, Saturn would float in that bathtub. Obviously, there are problems with that analogy, but hopefully you get the idea that, yes, in fact, Io farts on Europa. I will go with that. I am fully on board with that that analysis. Saturn So it is much less dense. But again, I just kind of skipped over its actual signature feature, um, which is that it has these immense rings. All Jovian worlds, all four of them, Jupiter, Saturn, Uranus, Neptune, all of them have rings. We didn't know that until the late 70s through the Voyager programs, because the rings of Jupiter, Uranus, and Neptune are so tenuous that they can only be seen, particularly Uranus and Neptune, they can only be seen through a phenomenon known as backscattering, which again, I'll go into the specifics later on. But Saturn has a huge ring, or at least a extended ring. In terms of its thickness, it's very, very thin. So here we're looking at it pretty much face on, and so you can see this nice vinyl record grooved sort of structure. But in actuality, if you looked at it edge on, it is exceedingly thin. It is made up of primarily of ice crystals, ice and dirt crystals that are roughly the size of a refrigerator. They're all being escorted along by shepherd moons. Those are the small little dots that you see in that disk. These moons, through their own gravitational influence, kind of keep these rings in line, literally in line. The open question about Saturn is, why does it have such an extended ring system? Because from a dynamical standpoint, we believe that, so for example, with Uranus, Neptune, and Jupiter, we believe the rings are caused from material from the moons being either being ejected in some way, either through tectonic activity, volcanic activity, or just asteroid impacts. So there's a small amount of material that gets ejected from these events, gets gravitationally captured, and forms these ring systems. But from a dynamical standpoint, that dust, because it's so light, is easily pushed around by things like radiation pressure or magnetic fields, things of that nature. So those rings will disperse over time. But the Saturnian ring, so what I'm getting at is the Saturnian rings, we don't think that the ring system should have a lifespan greater than 100,000 years or so, which leads us to two possible explanations. One, we're really, really lucky that somewhere within the very recent past, some event happened that created enough material to form this ring system, and it just hasn't dissipated yet. So basically, we hit the lotto in terms of getting into that 100,000 year window. Or there is another mechanism acting that is creating these ring systems that has yet to be properly identified or understood. So yeah, again, another open question. The only changes that Galileo saw was that Galileo was able to see the fact that the orbit of Saturn and the orbit of the Earth are not entirely coplanar. They are inclined with respect to each other. So what Galileo noticed was that the extent that you could see the rings changed over time. So it goes from which we see today. If you have a telescope and you have the time, you can see the rings of Saturn go from an orientation like this all the way through to sort of an edge-on perspective and then flip over. And that basically means that, if we take the reference point of Saturn, then the Earth is above Saturn at some points, and then the Earth falls below Saturn at other points. Oh, I have a picture of that. There you go. That's basically what that Galileo noticed with Saturn is we see this because of the fact that our position relative to Saturn changes over time. This is Titan, the largest moon of Saturn. I like to refer to it as Bizarro Earth. Titan is the only other the only other world in the solar system that has a thick atmosphere and also a liquid something on the surface. Now, while Jupiter or while Venus obviously has a very, very thick atmosphere, it does not have any sort of liquid component, liquid material on its surface. Basically, it's so hot that we're talking about temperatures in the range of around 400 Celsius or more. It basically would boil off anything on its surface. Titan, on the other hand, has a nitrogen-rich atmosphere, very much like the Earth does. Its density is very similar to that of the Earth, but and then when you look at the surface, we can see oceans, we can see rivers, we can see land masses I really should categorize them more as lakes than oceans, but we can see large extended bodies of liquid. We can see rivers, we can see mountains, that sort of thing. We see topography that is very, very similar to the Earth, but the bizarro aspect of it is that all of that is hydrocarbon. So instead of water, instead of carbon, instead of aluminum or aluminium, as you Brits might say, we're talking about a methane, ammonia, ice, and liquid methane, ammonia, and other hydrocarbons in there as well. No. Well, actually, Clive, if you want to, depending on how you want to define things, Enceladus, another planet of, Enceladus, another world or moon of Saturn, and Europa could theoretically be considered domed if you consider the ice sheet or the ice crust to be a dome on the top of an ocean or ocean mantle where life might be able to exist. The consequences of that, if you think about what a civilization would look like, or how deal with the fact that they are in a freely three-dimensional environment, and how they would perceive a dome, or possibly even perceive what is beyond that dome, is the stuff of sci-fi. Is just the stuff of really cool sci-fi, in my opinion, that no one really, in my opinion, has really exploited yet. This is, so we had a probe called Cassini. It went out to Saturn, very much like the Juno probe went out to Jupiter. It took close-up images of Saturn, we got some great science out of it. But not only that, it had a small little thing called Huygens, which basically is a lander. So by technical standpoint, the Cassini is a flyby or an orbiter, and then Huygens is a probe or a lander. Really, in this case, a craft. Actually, no, it did land. It did land. I'm sorry. Huygens did land. You could actually see the parachute fly by. And these are images of Titan as Huygens flew down through the atmosphere. And you can see those land masses that I was talking about, those geologic features that I was talking about. Roger and Mudflood University. Oh my God, I can't imagine what to me, these look like pennies, but I don't know. Roger might see, I don't know, giant feces or whatever. Yes. Oh, where is it? Oh, I'll be right back. There's a store in DC called Because Science, and you can get stickers like this. I don't know if you can see it, but it says Uranus is full of gas. Yes, that is the type of humor that I like, that I appreciate. Speaking of Uranus, here we go. You can see one of the rings. Let me make sure that it is actually Uranus. You can see one of those rings that I was talking about. Uranus is considered an ice giant for some reason. Well, the reason is that it has a slightly higher abundance of ices. It's cold enough that its upper atmosphere. The reason why it doesn't have the clear banding that Jupiter has, or even Saturn has, is because of this smoggy haze that surrounds it, that also has a lot of ice crystals in it. Now, there is a little bit of, I can see why there would be basically a subcategorization of the Jovian worlds. Jupiter and Saturn are significantly larger than Uranus and Neptune by a factor of 10 in both in mass and radius. So yeah, I can see that, and also because there are ice crystals in it. But you can see the ring for that. I haven't looked into this, but there was about sometime last fall, NASA was designing a probe for Uranus, and they put out a proposal for the public to name it. Now, if that probe is not named Buddy McAssface, I will lose my entire faith in humanity. I don't think NASA really thought through the idea of allowing the public to name a probe to Uranus. Just anyway. So this is blah, 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 Neptune. Neptune was known. This is a picture taken by Voyager. This is and sort of the iconic image of Neptune. It is with its great dark spot. Again, it is in this case, I believe it is actually sort of a hurricane. It is an anticyclonic storm. But again, the formation mechanism is very similar to what you find on Jupiter or Saturn, where you have bands of material that are moving contrary to one another, and it creates this spiral or this cyclone effect, this circular hurricane effect, anyway, rather. But unlike the Great Red Spot, we have evidence to let us know that the Great Spot has since dissipated. The Great Red Spot is, as far as we can tell now, no longer exists. It existed in the 70s, but by this point, it has actually dissipated. Here are Neptune's rings. Again, they are only seen from the back through a concept known as backscattering. Again, they were only first observed via Voyager 2. I think Voyager 2 was the one that went to all 4 planets, outer planets, all 4 Jovian planets, and basically was able to see that in the late 70s, early 80s, if memory serves. And then we get to Pluto. Remember that anecdote that I talked about where my department chair was like, why send a probe to Mercury? It's a rock. Who cares? Because of the possibility of this, we get to Pluto. Pluto, prior to the New Horizons mission, which took a really long time for it to get out there. I can't remember the number of years it took to get from point A to point B. It is the fastest moving object that humanity has ever produced. It's not moving at anywhere near relativistic speeds, but it is moving at a very, very high rate of speed. But it still took years to get out there. Now, prior to this, astronomers really had the best images that we got were from Hubble, and they weren't all that impressive. And based on the science that we knew at the time, the formation, basically how we think things would form out at that distance, we expected Pluto to be really unremarkable, just an icy covered dirt ball, really, or an icy crust over a rocky metallic core mantle combination. Boy, were we wrong. I mean, it is that in a certain extent. But what we got wrong was the fact that the Plutonian surface is so varied, so interesting. There is so much geologic activity on Jupiter that we never suspected. We really had no idea that this sort of thing could happen on a body like this, of this size. And we can only have known that by sending a probe that far out. I don't even think JWST, I'm sure they're going to, but and I may be proven wrong, but I don't think JWST could get images of this detail of Pluto. So we literally, it's so far away and so small that we literally, the only way that we can get good data is by sending a telescope very, very close to it, by sending past it. It certainly has driven a lot of interest of saying, hey, maybe we should actually pay more attention to these so-called dwarf planets further out. Now, I won't belabor this point yet, but the reason why I think, from a professional standpoint, that Pluto should be considered a planet is because, by my definition, the best definition that makes physical sense is a planet is something that orbits around a star that is spherical under its own mass. The reason why Pluto has been demoted, and why Mahe Mahe and Eris, my memory fails. There's like half a dozen other series in the asteroid belt. Why these are considered to be dwarf planets is because they do not satisfy the third condition, which is that they have cleared out their orbital path, that there are no objects of comparable mass in the orbit, in the orbital vicinity of that planet. Pluto does not qualify for this. There are other trans-Newtonian objects that are in the Plutonian orbit or near the Plutonian orbit that disqualify it. The problem with that is that it's location dependent, and that bothers me. If you took Pluto and you stuck it into the inner solar system, it'd be a planet. It would be massive enough to have been able to clear out its orbital path, because its orbital path would have been smaller, therefore less debris, easier to clear over time. So I have a problem with the idea that any definition is location dependent and not formation, based on formation or based on inherent physical characteristics. So this is a close-up of the Plutonian surface. So again, if this didn't grab you as saying, hey, Pluto isn't just a boring ice ball, you got this. I mean, this is you can see basically mountains, you can see plains. I mean, you have rich geologic activity happening on this world that no one suspected. And then finally we come to the I'm not going to be derisive about it. Well, maybe I am, and call it solar system debris, which a lot of astronomers think of it as. I know there is an entire rich field of astronomy that is small body astronomy that deals with asteroids and comets and meteoroids. The reason why we call them solar system debris is that these are believed to be very, very old objects. These are the primordial objects, the solid objects that condensed out of the solar disk just at the beginning of the formation of our solar system. These are the objects that survived being crushed into or ground into dust and blown away, but did not manage to succeed into growing into anything larger. With the recent probes being sent out to these objects, we are again learning far more than we are gaining better knowledge. We are learning that our conceptions or our ideas of what these objects are probably wrong, or need to be changed. This I can't remember. I'm a bad astronomer. I can't remember which one this is. But what I can tell you is this particular object was first hypothesized, or someone hypothesized that, hey, maybe this isn't a solid object. Maybe this isn't a rock or an ice cube floating through space. Maybe this is an amalgamation of smaller objects that are just gravitationally bound, and there just isn't any perturbation, there isn't any forces to cause it to get disrupted. So it's not solid in the sense of the Earth around us being solid. It's solid in the sense of billiard balls inside of the rack on a pool table. You take the rack away, these balls are just going to hang out unless something bothers them. And there's a sufficient enough gravity that it can keep its own kind of shape. And that what you're seeing here is there's a fine layer of dust surrounding it. Now that is aliens, yes. So that is that was one idea, but we really, until we actually sent out probes, it was a nice idea, but it really didn't gain any traction until really, really recently with DART. DART was a successful mission in that we were able to shoot a satellite at an asteroid and smash it into it and alter its trajectory. What it was able to do even further than that was that it smashed into it, and it illustrated that the impact, the characteristics of the impact aftermath, indicated that it hit into something soft, that it didn't hit into a really hard object. In that case, it would have produced a much greater deviation, deflection in its orbit, but it absorbed some of that impact energy, which would indicate that it is squishier, that it potentially is made up of, that it isn't a solid body, but rather made up of smaller bodies that are just enmeshed. Kind of think of, if you had a box that was just a styrofoam cube, you punch into it, you're going to make a dent. Now think of that same area or the same volume as packing peanuts. You can punch into it. You're not going to get to the bottom, but you're going to get deeper into that area, that volume, than if it were a solid styrofoam container, that sort of thing. So, and I think with that, I'm going to end my tour of this portion of the tour of the universe, and these are all various things. And the next time I pick this up, I will get into stars, galaxies, that sort of thing. But I really wish StreamYard had a dark view thingy. All right. I did say that I would talk about Zik Comet. All right, that didn't work. Images. How about, so this is a really cool image. Let's remove that. Present. Screen share. Tab. Let's go with that. Cool. You can all see that. Yeah, this is just Google. The name of this lovely thing. This is Comet C 2022. That means that was the year that it was found. E3, which I think is the designation of that, is the number of, that is not the first comet that was discovered in 2002, but I think it goes up to 1 through 9 and then goes to A and then repeats. That's where I think that's the way the nomenclature of comets works. And then ZTF is more than likely the initials of the discoverer. But you can see this is what it would look like if you were to look at it using a camera. I'm impressed with this thing simply because of the tail. A lot of these comets that get publicized, like these near-Earth or the comets that are going to be coming by the Earth, in my part, they look cool. They have this cometary coma, or they have this fuzzy coma around them, but the tails really never impressed me very much. Here we see, you can see that there are a lot. This has a very pronounced tail, and what we're seeing here is primarily what we call the dust tail. So when the comet proper, the nucleus of the comet, as it gets closer to the sun, it will heat up, and as it heats, it will begin to sublimate. So it's primarily composed of carbon dioxide ice. It begins to sublimate, but inside of that ice are heavier elements, basically silicates um, uh, and other carbon materials. And so when that dust or when that ice sublimates, it creates this puffy cloud, which we call the coma, surrounding the comet. And then those dust particles and the smaller ice particles that also kind of come off with it, they don't get completely sublimated, they get blown out by radiation pressure from the sun and create this very, very long tail in some cases. So now let's see if I can find. You can see how I find these things in a very professional manner. How about here? All right, so what are you guys seeing here? Let me visit this. Oops. Oh, no, you can't see that. Let me remove that. Let me stop screen. Let me present, share screen. Da, da, da. There we go. There is again another image of it. You can see the green, which is again because of the fact that that material that I was talking about, the dust that was in it, that isn't carbon dioxide. This is actually diatomic carbon that is being excited by the light. How long will the comet last before it's completely sublimated? That is an excellent question, Mark. Which I don't have a really good answer for you. What I can say is on the order of millions, possibly even hundreds of millions of years, because it is such a long period comet. The occurrences at which it basically erodes itself by coming by the sun are rare, or at least in terms of our lifespans. Like I said, I think that it has an orbital period in the order of tens of thousands of years. So it's going to take a very long time for it to erode or sublimate away. Short period comets like Halley's Comet and Hale-Bopp, they probably have lifetimes on the order of tens to hundreds of thousands of years. But I do have to admit a certain amount of ignorance when it comes to those sorts of timescales. Here we go. So what we're seeing here, comets are particularly long-lived comets that come from the Oort cloud beyond the Kuiper belt. They are very, very long, very, very old. All right, so what we're seeing here is a sky chart of or the path of the comet. Actually, I wonder if I could do this. What we're seeing here is, so this is February 1st, so it's located right about there. I don't know if you can see my cursor. I really hope you can. This is the Little Dipper. This is Polaris. So if you could find true north and you know your latitude, look true north and then go above the horizon, your latitude. So I currently live at a latitude of 40 degrees north, so approximately. And so I would look true north, and if I look 40 degrees above the northern horizon, I would find Polaris. If my sky was dark enough that I could see Polaris, I could see that it's the tail end of the Little Dipper. And then from there, I would go, I think, to the east. And that is where the comet is. But you know what? This is kind of a crappy way of doing this. Let's see if I can really break stuff and pull this up. All right. Maybe this is working. I'm trying to pull up Stellarium. I don't even know if it's working anymore because my computer is completely frozen. Well, it's frozen. Oh no, here we are. my laptop is very old, so you have to pardon me. But I'm hoping to be able to get Stellarium up and share that with you, and hopefully we can show you where I can show you actually where it is. Mm-hmm. 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 Aha. I agree. Allow. How about if I do it this way? Ooh, there we go. This is Stellarium Web. So, hey, look, it's the comet. Nifty. So this is, let me find my location. I haven't used this. Let's throw up some planets. There is the moon. Where's my location? Observe. Crud. How can I change my location? This is poopy. Just failed. How do I move this around? Here we go. All right. So this is Kings Park West. I'm assuming that's near me. So it'd be located right about there. So if you find the moon, the best way I can describe this is if you find the moon, which hopefully you can, you go down towards the northern horizon, and there should be a bright star, and that should be Capella. And then below, almost directly below that, will be the comet. Now, this is the problem. Like I said, the comet has right now a magnitude of 5.4. So it's not even fifth magnitude. So it's roughly maybe twice as bright as the dimmest thing that a human person could see in the night sky. So what I would suggest is finding a finder chart. Just Google Comet 2022 E3 ZFT and Google, and then finder chart. And hopefully you can find basically a chart that looks very similar to, let's see, go away, something like that. Make sure that you can see that. Something like this. I wish I could get Nathan to buy me a new PC. Something that looks like this. And so you can see various constellations like the Big Dipper, or Little Dipper rather. This is the Big Dipper down here. And let's see. There's Cepheus poking out up there. So if I were to, in this orientation, basically the horizon is at the bottom of the picture. So east would be to your right, west would be to your left. Technically speaking, well, going towards the south would be going up and around. So hail and Bob. See, to me, my favorite is always going to be Hyakutake, because that was the first astronomical object that I'm not surprised. The Hyakutake was the first comet, or actually the first astronomical object I ever took a CCD image of, and I helped create rather a mosaic of the tail. And I don't know if I could find something that will do it justice, because to me, Hyakutake comet. Hyakutake. Let me see if I can find an image of it that does it justice. There it is. That'll work. That one will work. Bam. Oops. Let me stop. Percent share screen. Tab. That one. Boom. Check that out. Is that APOD? No, this isn't APOD. This looks like APOD. Maybe not. Anyway, APOD. Astronomy picture of the day. Look it up. It's awesome. This is Hyakutake. Now, this is why it's cooler than Hale-Bopp. Hale-Bopp is cool because you can see the dust tail, but you can also see the ion tail, which is where the solar wind picks up electrons and protons and pushes those out. But you can see that here too. The ion tail is a little bit harder to see. It's this. And then you have the dust tail coming out here. But what's really cool is that you can see distortions in the dust tail. The tail was so long that the tail was actually interacting with inner solar system dust and gas and was causing the tail to break apart, which you couldn't see with Hale-Bopp. So fantastic. Also, in the image that I took, I don't know if it's in here. I think it's in or about there. You could actually see a tiny spiral galaxy. If I can, what I'll do is I will scan in my mosaic of it and try to show that because it's fantastic. I love it. Love. Oh, that's not what I wanted to do. All right, so. Oops, that's not what I wanted to do either. All right. All right. Thank you all for being here. I apologize for the whole music interlude debacle at the very beginning. If you saw it, if you were here at that beginning, I want to kind of go lay down and what's the word I'm looking for? Kind of conserve some of my energy because I really do want to get online and stream this evening during our public hours for the Great Great Comet observing tonight. I cannot guarantee that I will be allowed to control the telescope and actually take digital images of it, but I can at least spy on the group on the roof through our webcams, and I can just go off like I was before, talking about the comets and talking about that comet in particular. So I'm hoping that people will enjoy that, but as I said, I am fading. I need to go lay down for a while. We will pick up for those of you in my ASTR 111 class. The next lecture will be on Friday. You have a homework assignment due this week. Your first homework assignment is due this week on Expert TA. So if you have any questions about that, please let me know and I can work with you through it. All right. And that is it for me. So again, thank you very much for being here, for listening to me ramble on. It means a lot to me. And peace out, clear skies. And if you can, try to see the comet. I'm sure there will be live streams tonight for it. It's going to be around for a while. So hopefully, if not tonight, I can do a live stream where I can take digital images of it. So, all right. Clear skies. Peace out. Have a good one.